Right, so now we're going to start doing SN1, SN2, E1, and E2 reactions. From here on out, we're going to start doing these reactions that are basically big boy chemistry problems, right? So it's real chemistry, not the, acids and bases, or whatever bases, but we're going to start actually doing spicy boy chemistry. It's really good, really fun. So I believe that people learn more by doing practice problems, and as we do these practice problems, I'm going to be teaching you the material, right? So it's kind of like a lecture and just a little video for you to watch. So for these problems, I want you to say whether or not an SN2 reaction would occur, right? Would it take place in number 1? Well, you're probably wondering, what's an SN2 reaction? Well, an SN2 reaction is just, well, it's a one-step process. So it's one step, and you have to be an anion, right? So you have to be an anion. And that just means that you have to be what? That you have to have a negative charge. So you have to have a negative charge. And this really is, it occurs with allylics, and that's better than a primary, and that's better than a secondary, that's better than a tertiary, and that's way better than, let's see, way better than an aerial. Alright, so over here you should make a note that tertiary carbons and aerial carbons, so this would be an aerial carbon, right? They never occur. So you can say that over here, that tertiary carbons and aerial carbons, SN2 fails, right? SN2 fails because of steric hindrance. So that's due to steric strain. And yeah, it's important for you to know that steric strain does occur, but I'm not really going to get too much into it because that's really confusing. But just so that you know, let's say, for instance, hydroxide is negative, right? And when you have too many big groups clustered around you, like a tertiary carbon, it has a lot of groups attached to it, well, that causes some strain because those are electronegative, and whenever hydroxide gets near them, it's going to be repelled because a negative and a negative, well, they repel, and it's very hard for hydroxide to get into the little spot, right? So imagine that you're on a bus. If that bus has too many people, it's very hard for you to get in that bus, right? Let's say it's like jam-packed. Well, compared to the bus that only has a couple of people, well, it's easier for you to sneak on the bus and get to where you want to go. And so hydroxide has an easier time getting on that bus, getting on that primary carbon or allylic carbon, than a bus or a molecule that has a tertiary carbon or an aerial carbon, right? And you're probably wondering what's an allylic? What's an allylic? Well, allylic is just a, well, let's make a condensed one, I guess. Well, not condensed, but let's just make a molecule. And let's say that this is bromine. Typically, when you're doing SN2 reactions, you're working with halides, which include iodine, chlorine, bromine, fluorine, etc. Right? And so an allylic would actually be this. It would be this guy, right? And that's pretty good. Oh, sorry, not there, but rather over here. So yeah, don't get those confused, or rather over here, right? So what did I do? Well, allylic just means that there's a double bond, but it's not directly attached to the bromine or to your halide. So for instance, if you were to ignore this if you were to ignore that bond and you put a bond right here, well, that's a vinyl group. That's a vinyl group. And that's not really good. Sorry. A vinyl group, let's see, a vinyl. So a vinyl group is when a double bond is basically attached to the carbon. So if you were to do a blown up image, you have a carbon attached to a carbon, and that carbon is attached to a bromine, but this carbon right here is double bonded. And so that's really bad because it's very hard for you to kind of like yank this bond out of bromine. And you should know that SN2 reaction, well, it's not going to work. So vinyl never works for an SN2 reaction. It never works for an SN2 reaction. However, if you're working with alleles or allylics, well, it's going to work out. So you have something like this, right? And you have a bromine. Over here, that's allylic, right? And so this carbon that's attached to the bromine is not double bonded. But this carbon, which is not attached to the bromine, but it's like a neighbor, right? So he has to be a neighbor to this carbon, and he has a double bond. Well, that's really favorable. It's really favorable for bromine to be ripped off, and that's called an allylic. And you know, those are really good. They're super fast in SN2 reactions. Really good, really favorable. All right, so now you know what allylic is, and you know what vinyl is. Whenever we have a problem that has allylic or vinyl, I'll point it out to you, so don't worry. You're going to get a lot of practice, okay? You're going to get a lot of practice. Right, and let's see, what else can I tell you? Well, whenever you have an SN2 reaction, you're going to be having leaving groups. You're going to have leaving groups. And so let's say that you have a generic molecule filled with carbons and hydrogens. Let's call that R. Well, I'd rather have a leaving group that has an iodine, and that's going to be better than a leaving group with chlorine, or bromine, sorry. And that's better than a leaving group of chlorine, and that's way better than a leaving group with fluorine, right? And you can see here that whenever you have fluorine, chlorine, bromine, and iodine, that, you know, stability, or I should say reactivity, goes downwards, and bond strength goes like this. Not band, but bond. But why is that? Why is it a better leaving group? Why is iodine a better leaving group? Well, some people might say it's because of entropy, because iodine is bigger than fluorine. When it becomes solvinated, whenever the little water molecules surround it, that's what solvation means. It's going to take a lot of more disorder to completely surround iodine. And, you know, it's very confusing for me to even explain it to you. It has to do with disorder and like free energy and whatnot, but it's just ridiculous. If you want a simple way, well, you're going to say, well, you know, fluorine is electronegative, right? And so it wants to hold on to its electrons more than iodine. And since it wants to hold on to its electrons, is it really going to give it up? Is it really going to make bonds easily? No, it's actually going to retain its electrons. It's not going to make bonds that easily, so it's not going to be as reactive because, you know, it has a large electronegativity. It's a 4.0, right? Or you can say that because fluorine is so small, the bond length is really small. And since iodine is really large, it has a larger bond length. So let's think about sticks. If you had a large stick, right, and you were to break it, is it going to break easily? Like, let's say it's like a foot long and it's very thin. Yeah, it's going to snap easily. But if I were to give you a little tiny pencil, like a nub, right? You ever sharpened a pencil that it got down to its nub, and I told you to like break it, right, using your fingers? Are you going to do that? No, it's very hard. You can't even grab it correctly, let alone break it in half. So that's the fluorine. Since fluorine is so small, it's not going to be as reactive because its bond strength is really strong. However, iodine is a lot bigger. Because he's a lot bigger, he's going to have a larger bond length, and that bond length is able to be snapped in half quite easily. So since that bond length is able to be snapped in half really easily, he's going to be more reactive. So most of the time, you're going to be working with iodine, you're going to be working with bromine from what I've seen, and because bromine has a larger bond length, is going to be snapped easily, and because it's easily snapped, it can be reactive. So you're going to do a lot of reactions with that. All right, so that's kind of like the gist of SN2 reactions. It's not overly complicated. When we do problems, I'll just kind of like teach you as we go, okay? But for now, just know that to do SN2 reactions, you have to have a negative charge, right? And we'll get into these problems now. Let's bite in, right? So for number 1, we're working with iodine and water. Well, is this gonna react? Are we gonna do SN2 reaction? Well, say no, Brian. No. Shame on you. We're not gonna do SN2 reactions. In fact, the reason why we're not doing SN2 reactions is because water is neutral, right? We don't have a charge on water. Water is neutral. Whenever I write N, it's going to be neutral. And whenever I write AN, it's going to be anionic, aka negative, right? So this is neutral, and according to this guy, we have to have a negative charge. And so that's not a negative charge, right? So we're going to say no SN2 reaction. Okay, moving on. Now we have a bromine, sodium hydroxide, and is there going to be an SN2 reaction? Well, let's see. Sodium, if you rewrite this, you have Na plus, and over here you're going to have OH, and that's going to be negative. And so, yeah, the Na is just a spectator ion. And so in exams, it's really famous for professors to do this. They're going to put sodium or a metal like potassium or even rubidium, who knows? And that's just a spectator ion, so you could just ignore sodium. All you're really caring about is the hydroxide, and the hydroxide is negative. So yes, that is a negative charge. Okay, so after we found out that this is a negative charge, we're going to look at our substrate. That's just a fancy way to say what are we going to react with, right? And we're going to say, well, over here, we have a carbon, right? You agree that's a carbon, right? And it's attached to a bromine, but we have to figure out if it's a primary, secondary, tertiary, allylic, aryl, or vinyl. Is it vinyl? Is there a double bond right here? No. Is there, is it like a double bond like that inside like a cyclohexane or something? No, there isn't. So that's cool. Is there an allylic? No, that's not an allylic. So what is it? Well, yeah, it's actually primary. So that carbon is attached to another carbon that's primary. And you say, yeah, Brian, hey, SN2 reaction, they occur with primary and secondary, but not tertiary. Tertiary is garbage. Too much steric strain. We have a negative charge, and guess what? We have a primary carbon. Okay, so how are we going to do that? Well, over here, I'm just going to blow up this example, right? So here's how you do your reactions. This guy right here, that's a carbon skeleton, right? And so we're going to keep our carbon skeletons the same. So we have 1, 2, 3. We have 3 carbons, right? This bromine is going to kind of like kick off. He's going to go away. And instead, this, I'm just going to do out the curved arrows, right? So we're going to ignore the sodium hydroxide, just so you know. I'm doing the curved arrows because I don't know if that's going to be a free response question, and I want you to be prepared. Well, this bromine, oh, and by the way, this happens in one step, right? It looks like it's a multi-step reaction, but it's a one-step process. Well, this bromine is going to pop off. And notice that it's very easy for bromine to pop off because of the bond length, and the bond length is very long, so it's going to break off, so it's very reactive. So these electrons are going to pop off of bromine, and after that, we're going to have kind of like a carbocation. So this carbon has lost something, so he's a bit more positive. He lost some luggage, some emotional baggage, and he's a bit happier. But now, this other electronegative person, this negative person, sees that he's happy, and he doesn't like that. He says, no, I want you to be depressed and very sad. So he goes here, and he goes into the carbon cation. And what you have is an OH, right? And this bromine actually pairs with that sodium, right? And so that becomes your reaction. That's your reaction, right? Over here, we have a sodium and an oxygen. Well, that's sodium, and I should probably do that in a different color. It's attached to an oxygen. I'm not going to rewrite that whole molecule, but essentially this oxygen is negative, which is good. We want a negative molecule. And we have to look at our substrate now, because now we're thinking, okay, well, I have a negative molecule. I have to look at my substrate, whatever I'm going to react with, and I have to see if it's primary, secondary, or allylic. If it's tertiary, aryl, or vinyl, it's garbage, so throw it away, burn it. Okay, well, I'm looking at this carbon. We have 1, 2, 3. oh, great, garbage. It's bad. It's a tertiary carbon. So we can't react with tertiary carbons because it's going to have steric hindrance. And so that's really bad. So you're going to say no SN2. Say no, Brian, that's not SN2. Okay, that's not SN2 because of steric strain. That's steric strain right there. Okay, cool. Now over here, we have the sodium. And whenever it's a metal, like sodium or in that column, you're typically going to have a negative. So that oxygen's negative. Hey, that's pretty good. That's pretty cool, right? And over here, since we're negative, we're going to look at our reactant. And so we say, well, this carbon is 1, 2. Hey, Ryan, that's pretty good. We have a secondary carbon. All right, so now we're going to start reacting with our reactant. So we're going to draw the carbon skeleton. See, it's just I just copied down the parent chain. And notice that we're going to start reacting. And it's very important for you to know that this is a chiral molecule. Right, so it's a chiral molecule. If you want to assign prioritization, you start with bromine, you go to CH2 versus a CH3. I'd rather have the CH2, so that's 1, 2, 3, right? 3. So it looks like an R, but the hydrogen's in the front, so it's an S. So that's just kind of like a proof that it's a chiral carbon. And notice that this is only for chiral carbons, right? Notice that this was achiral, but SN2 reaction could still occur. Over here, this is chiral, and SN2 reactions occur, either or. But for chiral carbons, you have to do inversion. So when chiral, do inversion. All right. So what does that mean when I say inversion? Well, inversion means that this OH, or this oxygen with a methyl group attached to it, well, he's going to go in the back. He's going to do a back attack, kind of like a Pokemon. So that's a special move. He does a back attack. And the back attack, all you need to know is that you're just going to switch what you see here. So notice that my hydrogen is a wedge. Well, whenever oxygen does his special back attack and does like a critical hit on the bromine, right, that hydrogen gets transferred to the back. And so he becomes a hash. And this oxygen actually goes in the front. So you're going to have an O. And you might see a CH3 like this. Or I think it's a little pretentious, but I prefer to do this. So that makes a lot more sense to me. And notice that this was an S, right? We assigned prioritization. Well, let's do our prioritization, sorry, stuttering, right, to this molecule. So that's 1, 2, 3, and 4. And it turns out they have R. That's weird. And here's a really take-home lesson. Whenever you're doing a chiral inversion for SN2, right, if you have S, you're going to get R. So have S, has S, gets R. And what I'm trying to say is you're going to get the other letter, the other configuration after an SN2 reaction for a chiral carbon. So if I had R and I do a inversion because I have SN2, I'm going to get S. If I had S, I'm going to get R. And that occurs because of the inversion that we did, right? And that's kind of like a quick, skinny rundown on SN2 reactions and chiral inversions, okay? Cool. So what happens here? Well, let's see. We have potassium. Potassium's a metal, so that's for sure positive. And over here we have the whole group, and that's negative, right? Listen, I want you to pay attention to this. Whenever I do my reaction, I'm going to keep whatever is attached to that oxygen, right? I'm going to keep whatever is attached to that oxygen. So I'm going to keep the ethyl group. That's a CH2, CH3. That's an ethyl group. And where am I going to attack? Am I going to attack here, 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 where? Well, you say, Brian, that's obvious. You're going to attack the bromine. But hey, listen, is this a chiral carbon? I think it's a chiral carbon because we have a prioritization. Let's see, bromines is 1, 2, 3, and 4, and the H is in the back, so that becomes an R configuration, and so that is chiral. That's chiral. But is it a primary carbon or a secondary carbon? Let's see, that's a 1, 2, that's a primary carbon. But hey, Brian, I see a double bond, and that's kind of like a red flag for me. What's going on? Well, you're probably saying, oh, that's a vinyl group. No, it's not vinyl group. It's actually an allylic. A vinyl group would be if I had the double bond. Let's ignore this double bond. A vinyl group would be like this, or it would be like that. So that double bond is attached to that carbon, and that carbon is directly attached to the halide. Our halide in this case is a bromine. But because that double bond is attached to the carbon who is the neighbor to the carbon that is attached to the bromine, that is allylic. So what I'm saying is, you have a carbon right here, and then you have its neighbor. The neighbor has a double bond, and that's really good. We can borrow a cup of sugar from that neighbor. That's really good. And so that's allylic, right? So that's allylic, and that's going to be really fast. Also, whenever you form a cation, that's going to be a slow step. Okay, so that's a slow step whenever you form a cation, right? So that's going to be the rate determining step. Also, speaking of rates, you see I'm just kind of like spitballing this information, right? Whenever you see SN2, the reason why it's called SN2 is because it has, for the rate, it has that K. You're going to have your substrate. So for instance, our substrate would be like bromine, and it's also going to have our substrate of OCH2, CH3, etc. And so it really depends on the amount of bromine and oxygen ethyl group that you have. So if I told you that I increased bromine by a factor of 2 and increased oxygen ethyl, whatever, by a factor of 2, then what would I have? What's the rate? Well, I said that I increased bromine by 2, I increased oxygen by 2. What's 2 times 2? Well, that's 4, so the rate should double by 4 times. If I increased oxygen by 3, what's the rate? Well, 3 times 2 is 6, so it should be 6 times faster. And so that's what SN2 reaction is. And you should probably kind of like predict that E2 is the same thing. SN1 only has unimolecular, right? That just means it only has one thing in its reactant law. So yeah, that's kind of like a rundown for that. We'll talk more about that later. I just kind of want to hit on some key points. And so because we're chiral, we're going to start doing this. We're going to keep our chiral, we're going to keep our carbon skeleton like this. That's allylic. And we're going to do inversion. So this oxygen, well, first of all, this bromine, this bond goes to bromine, so now we formed a carbon cation. That's a slow step. It's very rate determining. And then this oxygen goes in here, right? Of course, this is just in an instant, like really quickly. Happens in less than a second. It's just one step for SN2. And notice that my hydrogen is going to go in the front because we're doing inversion, since this was a chiral carbon. So hydrogen is in the front. Whatever is in the back, we're going to have O, CH2, CH3. Another way you may see that is that you have a carbon, or you have an oxygen with an ethyl group, and then a methyl group, right? So that's an ethyl. Sorry, or rather that. There you go. So that's an ethyl group. And that's basically it for that problem. They're not too bad when you know what you're doing. Over here is just repetition. So this is a metal, so you're going to say, well, Brian, that's a metal. So that must be a carbon right here. That's a negative carbon. That's cyanide. All right, now we look at our reactant, and we say that this carbon is attached to one carbon, so that's a primary carbon. And primary carbons, they react, right? They react, right? So is the carbon doing the reacting, or is the nitrogen doing the reacting? Well, the nitrogen is not going to be doing the reacting. Actually, it's going to be the carbon, right? So that carbon is going to be right here. So we're going to do our carbon skeleton. This bromine popped off, and so do we have any chiral centers? No, we don't have any chiral centers, and so we just put carbon and nitrogen. You see? So our cyanide went and bonded, and now we have bromine with potassium. So that was it. That's an SN2 reaction. Over here, is this anionic? No, Brian, that's not anionic. This is actually neutral. That's neutral. Okay. So since we're neutral, you can automatically get rid of SN2 because the first requirement is that you're anionic. You have a negative charge. This one does not have a negative charge. This is neutral. Usually, you're going to have a metal group, and that really shows you that you're going to be neutral. This one is not neutral, but you're going to be anionic when you have a metal group. Since you don't have a metal group, most likely you're not going to be anionic. You're going to be neutral most of the time. So for these guys, we have a metal, 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 metal. Okay, so that's negative sulfur, negative oxygen, negative oxygen, negative oxygen, and negative oxygen. So that's An. So that's anionic, right? Okay, right. And over here we have a carbon, and that's a primary carbon. That's a primary carbon. Is that vinyl? No, the neighbor has a double bond, and so it's actually allylic. That's allylic, and it's really preferred, really good, super awesome. So what's the reaction for this? Well, the reaction that we're going to draw our carbon skeleton, and you're over here, and that bromine pops off first, and we have a sulfur with a hydrogen right there, right? So what we have now is that we have a sodium and a bromine pair. So that's an SN2 reaction. Allylic. Over here, this is negative, right? But hey, this carbon is primary carbon, so that's good. We should be able to do SN2. Say no, Brian. No, we're not. We can't do SN2. Why not? Well, that carbon has a double bond attached to it, and that's really bad. That's called a vinyl group. And for SN2 reactions, vinyls are complete trash and garbage. Throw it away. No SN2. No SN2 because we are vinyl. Cool. So this is negative. That's pretty good. Are we going to be reacting? Well, we have a secondary carbon. Am I going to do SN2? Say, yeah, I'm going to do SN2. Am I going to do it over here or over here? No, I'm going to do it with the bromine, right? He's going to be SN2 reacted. And so to do that reaction, we have our cyclohexane, and that bromine pops off, the oxygen replaces bromine, and it's going to carry the methyl group with it. Okay, so what about the other groups? Well, that's a negative, so it's going to react. But this carbon has 1, 2, 3. So that's garbage. It's a tertiary carbon, too much steric strain. So we say no SN2 because of steric. Okay, cool. And over here, well, Brian, that's a secondary. Should work. No, it's not going to work because of its aerial. It's aerial. So it has like an arena. That's an arene. So little electrons fight over here. So that's aerial. They're fighting because they want SN2, but they don't get SN2 because it's a ring shape with double bonds all around. So that's aerial. No SN2. Aerial. Now I want you to tell me the reactivity of these molecules when I react them with sodium OCH3. Well, first of all, is it going to be an SN2 reaction? Well, let's find out. Over here we have sodium, and he's positive, and if that's positive, then oxygen has to be negative with a CH3. So yeah, that is possible for SN2 reaction because he's negative, it's an anion, but now we have to look at the leaving groups over here. Okay, over here. So when I want to rank the best molecule, right, so the reactivity, 1 being the highest reactivity, 4 being like the lowest, or 6 being the lowest, I should say. Well, like I said, when we have fluorine, chlorine, bromine, or iodine, and we have to figure out which one is going to be more reactive, well, I'm going to be looking down the line. So iodine, or iodine, whatever you prefer, is going to be more reactive. So automatically, he should be number 1. So bromine is not going to be number 1, but iodine is. Okay, well, do I want a primary iodine, or do I want a allylic iodine? Notice that this double bond is on the neighbor carbon, and he's not directly attached to the parent carbon, right? So if we had the red bond instead of the black bond, then that would be vinyl. However, we have allylic. So which one do I prefer? Allylic or primary? Well, I'd rather prefer the allylic. So that's going to be number 1. That's going to be number 1. Well, iodine is better anyway, so that's going to be number 2. Okay, and now we're going to bromine. So bromine, well, let's see over here. Do I see any allylic bromines? No, this is vinyl. That's not allylic. Do I see any primary bromines? Hey, that's a primary bromine. That's primary. That carbon's only attached to that carbon. That's primary. So that's going to be number 3. Let's see over here. That's 1, 2, 2. Where do I want this? We have 1, 2. That's a secondary carbon. That's a secondary carbon. Where do I want this guy? Let's see over here. Well, he's also primary. So you're probably wondering why I chose him over this guy. Well, he's bigger. Shouldn't he be better? Well, that's the problem. He's bigger. He has an extra methyl group attached to him. That's not really good, is it? Yeah, we're primary, so we should be fast. But when in doubt, go with the smaller guy, right? It does matter because SN2 is really sensitive to steric strain. And so do I want a lot of groups that can block me? Or do I want few groups that can block me? Number 3 had a little bit of groups to block the OCH3. But this one has an extra methyl group that can potentially catch the OCH3. And because it has an extra group, that's not really favorable for SN2. So yeah, it's still going to react. It's just not going to be as good. So we're going to say that this is number 4. All right. Over here, that's a secondary carbon. So that's going to be number 5. And yeah, this is dead last right here. This is actually a vinyl group. And vinyl group are absolute garbage. So that's vinyl group. It's bad. That's going to be 6. Okay, so now we have to find out when reacted with this guy, which one is going to have more reactivity. Okay, well, is SN2 reaction possible? Over here we have a negative H2O, or not oxygen, but NH2. It's negative because of that metal group. Then we have a negative oxygen with a methyl group. And then we have a negative oxygen as well. And then we have a neutral OH. So first of all, if I'm ranking from 1 to 4, this is going to be number 4 because it's not even negative. It's neutral, right? There's no metal group. Now we have to figure out which one is going to be number 1. Is it this guy? He looks pretty good, but he's not. He's not that. So the reason why this one is number 1 is because nitrogen is less electronegative than oxygen. Now it's very non-intuitive. It's very like, oh, that's the opposite of what I thought. Well, that's the point. Nitrogen has little electronegativity when compared to oxygen. And because it's less electronegative than oxygen, it's going to be more reactive. So just remember that less electro, that gives more reactants. Okay, so that's going to be number 1. Now compared to this oxygen versus that oxygen, which one are you going to say? You're probably going to say, oh, this one has resonance and it's going to be more stable, more reactive. No, that's the problem, dude. That's the problem. If someone is stable, are they going to yell at you? Are they going to be very reactive? No, because they're stable. They're very happy. They're great. And because that person is stable, they're not going to be reactive to you. This oxygen does not have any resonance. And because it doesn't have any resonance, it's not going to be as stable. Because it's unstable, it's going to be more reactive. So this one has stability and it's not as reactive, right? But it's still better than this uncharged molecule. And so you can think of resonance. I really butchered that. Resonance equals less reactivity. That is a happy face. Now this is like a super famous topic to be on exams, right? I'm not saying that this question is going to be on the exam. I'm just saying that this type of question could be on the exam. So it's asking, we have our reactant and we have to get this product. How am I going to get that product? Okay, well, it's pretty simple when you think about it. Notice that this is a chiral carbon, by the way, and that this hydrogen came into the front and this bromine left, right? So this, whatever that is, I'll tell you what it is in a little bit, came in the back, so it did a back attack. What is going to allow us to do that? Well, what's going to allow us to do that is that you could have a sodium sulfur phenol. The pH just means phenol or phenyl. I should say phenyl. That's what pH stands for. I'm not going to draw the phenyl out, obviously. So you can have a sodium phenyl, and that sodium is going to be negative. And so that reaction could go as follows. This bond breaks off and gives electrons to bromine. We form a carbocation. This sulfur is going to be attracted to that negative or to that positive zone. He's going to go over here. Now we're going to go in the back. So this hydrogen flips forward and goes in the front, and our sulfur phenyl goes where the hydrogen was, and that's just inversion. Now let me give you a proof. So this bromine, let's say that's number 1, right, in prioritization. That's going to be number 2, it's 3, and that's 4. So that's 1, 2, 3. That's an R configuration. Hydrogen is in the back, so we keep it in an R configuration. Over here, we have a sulfur, which is quite large. That's 1, 2, 3, and 4. That's going to be R configuration, but the hydrogen is in the front, so we're going to switch it. Instead of this, we put our arrowhead on the other side, and we call that an S configuration. So that's an inversion in stereochemistry, just for SN2 reactions. And this is SN2 because this is an anion that's negative. You have a 1, 2, a secondary carbon. That's going to be a secondary carbon. And so yeah, that's going to be really good for SN2 reactions. Okay, moving on, we have this weird, funky looking group. Over here, you can have that a sodium. It could be potassium or rubidium, doesn't matter. I just like working with sodium. We have a carbon negative. Oop, that's a positive, sorry. And that's going to be triply bonded to that carbon with a phenyl group. So that's all that happens. This is a primary carbon. So is it chiral? No, it's achiral. But notice that SN2 reactions could still occur. They're just not going to have any stereochemistry. They're not going to be inverted. It's very simple. This bond breaks over here to that bromine, and this we form a carbon cation, and that negative carbon is going to be attracted to this positive zone and attach itself. That's what you see over here. And this all occurs in one step. It happens really quickly in a snap. And yeah, it just happens in one step. It's very simple if you know the mechanism. Now we're going to be kind of recapping before we finish SN2 reactions. Yep, that's it. I'm finishing SN2 reactions pretty quickly because we have a lot of material to cover. So hopefully this wasn't too hard for you to grasp, right? Is an SN2 reaction going to occur for these molecules? Let's see. This is a negative, so that's sodium's positive. That means oxygen has to be negative. Oh, that's a metal. That's potassium. So this is a negative. That's cyanide. This is hydroxide. Now we're going to look at a carbon. That's a primary. Oh, that's a secondary. Okay. And what about this carbon? Let's say 1, 2. So both of these guys are going to be secondary. Okay, cool. So secondary and anionic, aka negative, that's really good for SN2 reactions. So yeah, we're going to do SN2 reactions. But hey, are we chiral? I think we're chiral. I think we are. Let's double check. Let's see, this bromine is number 1. That's going to be number 2, 3, and 4. So that's going to be, that's an S configuration, but our hydrogen is in the front, so it's going to be reversed. That's going to be an R configuration. It's going to be R configuration. Okay, so we draw our carbon skeleton first. Notice that it was a butane, and so I just drew my butane, and now I'm going to do what? I'm going to be reacting. And I like saying these kind of like mechanism steps for you to kind of understand what's happening. So this bond breaks and goes to bromine. Okay, so now we form a carbon cation. That's really slow. We don't like carbon cations because carbon wants 4 bonds. Ripping off a bond gives us 3 bonds for carbon. That's really bad, and carbon doesn't like that. That's why it's a really slow step, right? It's kind of like going up to a 2-year-old who's watching a YouTube video, probably one of my videos if that is a smart baby or something. But most likely that baby's watching one of my videos on YouTube and he doesn't want to get rid of that phone, so he's going to cling on to that phone. And so taking that phone away from him or from that baby is going to be very hard to do. So taking that bond away from carbon is very difficult to do because carbon always wants to have 4 bonds. Forming a carbocation is very slow. It's going to be the rate determining step. So right here, this is a 1-step reaction, by the way, not a multi-step reaction. SN1 is going to have multiple steps, but SN2 only has 1 step. So this, what I'm doing, occurs in like a millionth of a second. It's really quickly, okay? So the bromine pops off. We form a carbocation. That oxygen is like, ooh, a positive, and he goes over there. But since this is a chiral molecule, what was a wedge becomes a hash, and so that hydrogen, which was a wedge, becomes a hash, and whatever was a wedge becomes a whatever was a hash becomes a wedge. So that bromine popped off. Instead of being a hash, we're going to be a wedge, so that becomes a oxygen right there, a hydroxide, if you say. So basically, this hydrogen stayed, but it got turned over, right? And so this should be an S configuration. So that's a 1, 2, 3. And notice that's over here. That's 4. So that's going to be what? Counterclockwise, that's an S configuration. Very cool. Or over here, we have a potassium and a carbon nitrogen. So that's cyanide. Well, it's going to be negative, so that's good. That's an anion. That's a secondary carbon, so that's good. Where are we going to react? Are we going to react with this carbon? Say no, we're not going to react there because it doesn't have a halide. Notice that I'm working with halogens, fluorine, chlorine, bromine, iodine. Well, those are halogens, and so we're going to be reacting with them exclusively for SN2. Okay, so again, this bromine pops off. Notice that this is actually chiral, right? There's no symmetry. It's 4 different carbon attachments, so it's chiral. He breaks off. We form a carbocation. This carbon goes to the carbocation. Notice that since we're chiral, the hydrogen, which was a hash, is going to be a wedge. And so let's draw our pentane group. Notice that nothing happened over here, so we should still have a methyl group. We should still have that. And a hydrogen. Nothing changed at all. Nothing changed. This bromine is actually, this bromine pops off. And I should say that you're pairing with a sodium bromide, most likely. And over here we have a methyl, not a methyl group, but over here we have a hydrogen, which was a wedge now, and in the back is going to be carbon nitrogen or cyanide. And so that's just inversion of the stereocenters for chiral molecules. So now what happens? We have a product, but now we don't know our reactants. So what can I make? What kind reactants can make this product? Well, whenever I'm doing an SN2 reaction, I'm not going to be messing with the parent, right? So I'm not going to be messing with him. And so it's pretty safe to say that whatever you're not messing with, you're going to use as a reactant. So I'm going to have my pentane, my cyclopentane over here. Am I messing with him when I do the reaction? No. Say no. We don't mess with him. We have a methyl group, and over here we're going to have an oxygen. That's going to be negative, right? It looks like a square or something, but it's actually a pentane. I'm just really bad at drawing, okay? And now we're going to need something that's negative. So I'm going to have a metal. And you can have a halogen. I've seen that we've been working with bromine a lot, so I'm just going to do bromine. So we have a bromine, but that bromine has to bring something. He has to bring 3 carbons. And so you can say that this is a CH2, CH2, and then CH3. So you see a CH2, CH2, CH3. And so you could play this reaction in your head. You can say that this bromine, which is negative, is actually going to pop off right here. And now this carbon is going to go over here and merge with that oxygen. And notice that this is a completely valid operation. Notice that oxygen only had 1 bond, which is unfavorable. Now oxygen has 2 bonds, which is super favorable. It always wants 2 bonds. And this bromine is going to be paired with this sodium or whatever, and they're going to go somewhere else. But that's the reaction, basically. And so the thought process that you should have on this one is that oxygen is going to be on the main parent chain, which is a cyclopentane with a methyl group, and it's going to be negative. And it's going to be negative because it wants to attract this positive carbon, right? And so this positive carbon is going to go into this oxygen, and it's going to do that via SN2 reaction. So the main thought process that you should have is draw the parent chain, maybe put the reactant over here, and just try to figure out a reactant that would actually allow you to do this via SN2, SN1, E1, E2, whenever you get to that, right? So these are actually the hardest ones because you actually have to double guess, and that's probably going to be on the exam. Probably do more practice problems on that one on your free time, but that one's like the most difficult one that could be thrown at you. Also, this marks the conclusion of SN2 reactions, so I'm very proud of you for making it that far. And after this one, we're going to do SN1 reaction, so I hope you're ready to learn some big boy spicy chemistry. Very fun, very quick, and I hope that you understand SN2 reactions a lot better. Now begins our transition into the SN1 reaction. So SN1. Well, first off, this is a multi-step process. So multi-step. And since it's multi-step, I'm actually going to take my time doing these reactions, if there is a reaction, with you so that you become accustomed to the reaction process for SN1. Notice that this is an SN1, so you see a 1 right there. That means that the reaction actually, for the rate, for the reaction, you're going to have some K value. It's not very important in this class. But for the substrate, which means that whatever we are reacting with, well, we don't care about it. We don't care about it. We only care about, what we're reacting with. So, for instance, water, if you remember Gen Chem 2, it's a liquid. And we don't care about liquids or solids in our reaction process. And so the only thing that we care about is going to be the iodide or whatever. And, well, it's just one value. So if a problem says, in an SN1 reaction, we increase the iodine concentration by 50 kajillion, what is the rate? Well, the rate is going to increase by 50 kajillion because it's only one individual that really matters, right? So that's also called unimolecular. And SN2, which relies on 2 substrates, is going to be called bimolecular. And notice that this is not squared. So if you have something that's bimolecular, that's not going to be squared. Bimolecular means that there's going to be something else, like chlorine or something. And unimolecular It just means that it's by itself. So you never have squared or cubed or whatever. It's always just by itself. So that's unimolecular. Then you can have like R carbon. That's going to be bimolecular. So that's SN2. And over here is going to be SN1, right? So that's a multi-step process. It's unimolecular. And the most important thing that you have to know is that it's going to be neutral. It's going to be neutral, right? So in SN2 reactions, you had sodium hydroxide. Hydroxide is negative, but SN1 reactions are going to be working with neutral molecules, neutral. And very similar to SN2, allylics are super good, but very opposite to SN2. Tertiary is going to be great. Secondary is going to be good too, but it's really better than primary, and that's a lot better than aerial, right? So again, over here, primary and aerials, well, those are garbage. So that's garbage, and those never react in SN1, right? So what does that tell you? Well, it tells you that aerial for SN2 and SN1 is bad, and it's never going to react. And it also tells you that allylics are going to be really good in both cases. And it also tells you that secondary carbons can be either SN1 or SN2. And so sometimes when you have a secondary carbon, well, you're going to have to look at whatever you're reacting with. Is it negative? If it's negative, then it's going to be SN2. If it's neutral, then it's going to be SN1. All right. So that's kind of like the skinny, just kind of like the rundown of what we're doing. Right. And of course, the leaving groups are going to be the same pattern. So I'd rather have a iodine leaving group than a chlorine leaving group, or sorry, a bromine leaving group. And that's better than a chlorine. That's better than a fluorine, right? So now we can get on to the reactions, right? Over here, is that an SN1 reaction or is it SN2? Well, let's see over here. Well, that's neutral, so that's N, neutral, and you know that's pretty bad for SN2, but I think it's going to be what? SN1, right? Well, you say, Brian, no, that's not right, because to be SN1, it has to be greater than a primary carbon. Let's see, that's 1. Hey, that's a primary carbon, and that's pretty bad for SN1. Because I'd rather have a tertiary carbon or a secondary carbon, or in the best case scenario, just between you and me, don't tell the others, I'd rather have an allylic. But a primary carbon is garbage, it's just bad. And so since it's a primary carbon, you're going to say no. No SN1 or SN2. Right? Okay. So what about this one? Well, you have a sodium and a oxygen. Well, sodium is positive, and that means that this oxygen is negative. And for SN1, am I going to be working with negatives? No, you're going to be working with neutrals. And so automatically you're saying no SN1. No SN1. Okay, because that is negative. Well, let's see, 1, 2. Hey, that's a secondary carbon. And over there, you're going to be working with actually SN2. So that's actually going to be SN2 because you have negative and what? It's a secondary carbon. And we already did that problem, but if you want to do it again, I recommend that you do it on your own, right? Just to see if you're doing good. And here's a hint, it's chiral, so it's going to have some inversion, right? Now over here, is it negative or positive? And notice the pattern that I'm doing. Am I looking at this first? No, because the major determinant, this is by priority, the major determining step is, or the factor, not the step, sorry, is going to be the negativity of this guy. Is it positive or is it neutral or is it negative? So that's really what I'm basing my thought process on. So over here, if you did the math, if you did the calculus, right? Well, this is actually neutral. So that's going to be N, neutral. And since it's neutral, automatically you cannot do SN2. So this is possibly SN1. But you have to check over here. So we have a what? A 1, 2. So that's a secondary carbon. And hey, we can clap. We can do SN1 reactions. But Brian, isn't this like a chiral carbon? And I would say, yeah, anonymous person, this is a chiral carbon. So do we have inversion? Well, actually you have a racemic mixture. And we call that racemic mixture means that you have a 50% chance of getting an R configuration or a 50% chance of getting an S configuration. Now, the reason why this happens is because whenever you rip off a substituent, it's going to be kind of flat. And because this molecule is flat, this guy can either go from the top or the bottom, and depending on its orientation, it can give you a different configuration. And I didn't mean for that to rhyme, but it did. So that's pretty good. Okay, so here's what you do. So for this one, you're going to have two possibilities, and all you have to do for this one is draw out the carbon structure, the carbon skeleton, and yeah, you can have an inversion for the hydrogen over here and a wedge for the OCH3, and then you can have another one, so you can have OR, right? And we could keep this hydrogen in the front, right? We could keep that hydrogen in the front, and it could actually come in the back. So that's going to be a OCH3. So sorry, my apologies. That's CH3. Okay, so that's like the main product. Notice that one of them is going to be R, the other one's going to be S, and just to kind of save you some time, is going to be like this. So that's going to be R, but the hydrogen is in the front, so it's going to be S. Over here, that's going to be 1, 2, 3, and 4. Hydrogen is in the back, so it turns out to be this way. That's going to be R configuration. So let's say that this is R. And over here, we have 1, 2, 3, and 4. So that's also R, but then hydrogen is in the front, so we're going to have to reverse our arrowhead. That's going to be S configuration. And so notice that you're going to have a racemic mixture. That sometimes, notice that for this one, we started off as S. We can also have another S, but we can also have the possibility to make an R. That's what it means by racemic. And so for SN1, you're going to have a combination. You're going to have a blend. This blend does not occur in SN2. You're always going to, for SN2, if you have an S, you're always going to get an R. If you started with an R, you're always going to get an S. For SN1, if you start with an S, you can make another S, or you can make an R. If you start with an R, you can make another R, or you can make an S. So the real kicker for this problem is the process. And notice that this is a multi-step process. What do I mean by a multi-step process? Well, I'm saying that for SN2, it occurred in one step. So everything you saw, the small steps that it broke into parts, it didn't really occur. It just happened in an instant. But for SN1, you're going to have multiple steps. In fact, you're going to have 3 steps. Okay? So what are those steps? And what happens? So we're going to draw our carbon skeleton again. And what happens? Over here we have bromine. And we're going to be treating it with this solution for OCH3. Okay, so what happens here is that, well, I'm only going to do one of them, or you know what, I guess I'll do both of them just to kind of make you feel special. So what happens here is that this, for instance, this bond over here breaks because it's very weak. It's going to be more reactive, and it's going to break towards bromine. Okay, so now that's step 1. We only have the hydrogen over here. And notice that we made a carbocation. So what does that tell you? It shows you that this is a slow step. This is going to be the rate determining step. And I already told you, because carbon has 4 bonds and we ripped one off, carbon has 3 bonds. Not very favorable, not very good. It's not going to be happy. So it's going to be slow to do. Okay. After that, this oxygen is going to be very attracted to this positive center. And it's going to connect. Okay, it's going to connect. And so when it connects, you're going to have a hydrogen, and then guess what? You're going to have a hydrogen, oxygen, and a CH3. And so this oxygen is actually connected to that wedge, not the carbon, okay? So that's step 2. This is kind of like a proof of the carbocation. Normally you don't see that. You just see the substituent or the substrate react with this guy. You see this guy instead. Okay. And of course, this can occur on the other side. So hydrogen could be in the back. We're going to do it again, doing the other inversion. So that's step 2. But do you see the problem here? Well, the problem here is that that oxygen is attached to a carbon. It's also attached to another carbon, and then it's attached to this oxygen, or to this hydrogen. And so in total, this hydrogen is attached to 3 things. Do you see the problem? Well, oxygen really likes to be with 2 bonds, not 3. So it's bonded to a hydrogen, it's bonded to a carbon, and it's bonded to another carbon, which happens to have 3 hydrogens, right? So I have to do something. Am I gonna shoot off a methyl group? Is this guy gonna shoot off? No. Is he gonna shoot off this entire guy? No, because he wanted to connect. And so what's gonna shoot off, what's gonna pop off, is this hydrogen. And so step 3 is just really the hydrogen group shooting off. So shooting off somewhere, right? So notice that this hydrogen disappeared. So that's going to be step 3. And so our product, that hydrogen is going to connect with this lone bromine. So that bromine popped off somewhere. This hydrogen actually popped off too, and they're going to connect to make HBr, okay? And so that's going to be your reaction. And if you want me to do it using the other inversion, and so kind of like a recap of what is possible, over here we have our carbon skeleton, we have the original hydrogen and the bromine. We're going to be treating with some hydrogen, CH3, and oxygen. Okay, so first of all, this bromine pops off, and then you're gonna, what? Since you want hydrogen in the back this time, you're gonna have hydrogen over here. That's step 2. That's step 2. This hydrogen is gonna pop off from the oxygen, and let's put a bromine over here, just kind of waiting out. The hydrogen is right there. And then this hydrogen pops off and goes with that bromine. And notice that I could do it either way. So I could do one R and I could do the other one S, right? And that's kind of like the reaction. And if you want me to do kind of like repeating this reaction for the other problems, it's going to be a pain for me to do it. But hey, I love you guys. I love you personally. Just don't tell the others. And I seriously mean that. But I'm going to keep doing this reaction so you can understand the mechanism and so that you can actually repeat it during the free response, because I know that this is a possible free response. I could just feel it, you know? It's always a free response. So that was an SN1 reaction. Is this an SN1 reaction? Well, you say, no, Brian, this is not an SN1 reaction because this is negative, or so that's positive, and this oxygen has to be negative. If we're negative, then it's going to be SN2 reaction, most likely. The further we go along, you're going to have more options, and sometimes one of them fails, so you're going to have to go to the other option. But in this case, we're only working with SN2, SN1, right? So this is not SN1 because that's negative, and you have to be positive, or sorry, you have to be neutral. So most likely it's going to be SN2. Let's see, 1, 2, and 3. So that's tertiary. And hey, is SN2 reaction going to work for tertiary? You say, no, Brian, that's not going to work. That's going to be garbage. That's bad. And so there's no SN1 or SN2. Well, later on you're going to learn about E1, E2. And that might work for us, right? So over here, this is not SN1. So no SN1 or SN2. So no reaction for now, right? What about this one? And by the way, this is not SN1 or SN2 because this is negative, so it automatically cannot be SN1, but this is tertiary, so it cannot be SN2, right? Over here, what is it? Well, is it negative? Say no, it's positive. There's no metal, right? So that's just a hydroxide group, but it's attached to this guy. So, yeah, so it's going to be neutral, so it looks good for SN1. But what about this? 1, 2, 3. And hey, that's pretty good. A tertiary carbon for SN1 is really good. And so yeah, that actually would react for that one. Okay. So do we have to worry about stereochemistry? Well, no, I would say that you don't have to worry about stereochemistry. The reason why is because we don't have a chiral center. Okay, we don't have a chiral center. So I only did that reaction because that has a chiral center, and so I did it like 2 ways, but this one has no chiral center. It doesn't mean that SN1 or SN2 is not going to react or happen. It just means that you're not going to have any inversion, right? So the way you do SN1 is that you draw your carbon skeleton right there, right? And that looks pretty bad. Okay, and this is a bromine. That's going to be kind of like a oxygen right there. Okay, so what happens? Well, what happens is that this guy pops off. So you have, let's do this. You have a carbocation, but then this oxygen is going to go over here and kind of like form a bond. So he's going to form a bond to make it a little bit more obvious of what I'm doing. Looks pretty weird, but it's what happens. So that's going to be step 1. This is going to be step 2. But notice, oxygen has 3 bonds, and that's pretty bad for oxygen. It wants 2 bonds. So am I going to shoot off this guy, or am I going to shoot off that guy, or am I going to shoot off the hydrogen? Well, you know, I'm going to pop off the hydrogen. That's going to be really kind of like prime for popping off. Also, there's a bromine just hanging out right there. It could just, you know, it kind of looks like it's attached, but there's a bromine just hanging out. So I'm going to take off this hydrogen. And what I see over here is I have an oxygen that's double bonded to this, well, it's not double bonded, but it has that guy. And you just have a bromine attached to a hydrogen. And so that should be your main structure. So this is going to be step 3. Right, so that was a multi-step process. First of all, the bromine pops off because it's very reactive. We form a carbocation, so step 1 is going to be the slowest step. This oxygen is going to be very attractive to that positive zone, so it's going to connect. Everything is going to connect, but this hydrogen is still connected to that oxygen, and that makes us have 3 bonds, which is not ideal. It's not good, and so oxygen is going to shoot off that hydrogen that's attached. And so that hydrogen is going to go and merge with that bromine, or I should say that bromine is going to merge with that hydrogen, sorry. And so they're going to make HBr, and that oxygen now has 2 bonds, which is very good. And that's SN1 reaction for that problem. And I hope you understand SN1 reactions just a little bit better than what you did yesterday, right? Okay, but what about this one? Are we neutral or are we negative? Well, we're neutral. And so for sure, since we're neutral, we have to do SN1, most likely. So now that we consider SN1, we're going to look at our substrate. So over here, that's a secondary carbon. So that's pretty good. And hey, notice something. Is this vinyl? Say no, that's not vinyl. Vinyl is when you have a double bond directly on your carbon parent. Well, that's on our neighbor. And so our neighbor has a double bond. And if it's a double bond on a neighbor, that's going to be called allylic. And if it's allylic, that's really good. It's really ideal. So that's going to be really fast. That's going to be a fast reaction. Okay, and we are chiral. I hope you can see that. We are, let's see, that is a R configuration. It's going to be R configuration. Okay, so we're going to have to kind of do this again. So of course, I'm not mad at doing this. It takes a lot of time, but I hope you understand what you're doing now. So it's going to be a bromine first. Let me erase that. That's a bromine. That's a hydrogen. And we're going to be reacting with CH3OH. Okay, Well, first of all, this bromine pops off. That's going to form a carbocation. If you form a carbocation, it's going to be very slow. So that's a slow step. That's going to be step 1. That's going to be step 1. Okay? And afterwards, you're going to put the oxygen. That oxygen is going to be very attracted to that carbocation. And so you have 2 ways to do that. I'm going to do both ways. Very slow, right? So let's make it go on the wedge first. So we have an oxygen with a hydrogen. Everything moved with it. Okay, so that's going to be step 2. Right, but oxygen is now attached to 3 things. It's attached to that carbon, it's attached to this carbon, and now it's attached to that hydrogen. And so when it moves out, it's going to have an oxygen and then H3 and C. Notice that this hydrogen did not move, right? But the other hydrogen, sorry, I should have a bromine just hanging out. That hydrogen that popped off, the bromine is going to collect it and it's going to form an HBr. Okay, and so this is the reaction process for that. And notice that it could go in the reverse section. So when I say reverse, I mean inversion, because we are chiral. So we can have something like this. Notice that this hydrogen was in a dash. It's going to go in the wedge. And whatever was over here, you're going to have this guy. Pretty cool. So we're going to have HOCH3. And again, hydrogen wants 3 bonds. It wants 2 bonds. It has 3 bonds. Not good. So that H still stays the same. That hydrogen pops off. You're going to have an OCH3 and then an HBr. Okay. So that's the process. If you want arrow pushing, you can, right? With arrow pushing, you're going to connect this guy over here, right? And then this this bond goes right there, and that bromine picks up this hydrogen. Pretty messy, but that's basically the arrow pushing. If you get used to it, it's not that good. But yeah. Anyways, for the second one, or for the 7th one, is a reaction going to be possible? Well, you better say no, right? Or I'm going to cry. Because that is actually a vinyl. And it's a vinyl because it has a double bond directly connected to our parent carbon, to that carbon. And so it would not be a vinyl if the carbon over here had a double bond, right? So our neighbor does not have a double bond, but we ourselves have a double bond. And so that is not good. Even though this is neutral, and you would say, oh, SN1. Well, vinyl is still trash for SN2 and SN1. Same thing for aerial, right? And that is not good. So we're going to say no, SN1, because of the vinyl. Okay, that's the vinyl. Over here, what's going to happen? Oh, you're probably saying, oh, it's aerial. Well, it's not aerial. Why is it not aerial? Well, because this does not have double bonds. An aerial carbon actually has double bonds around us, right? So it's kind of like a phenyl, but it's not. So it's just a simple cyclohexane. It's going to be SN1 because this is neutral. That's neutral, so it's going to be SN1. And the way SN1 happens is this chiral? Say no, it's not chiral. It's going to be achiral because you don't have a unique stereocenter. And so since it's achiral, you're not going to have any inversions. And so this bromine pops off first, right? And that's going to be step 1. And step 1, you form the carbocation, so it's going to be a slow step. It's going to be step 1. Step 2 is that this water molecule connects. Right? We have bromine. Let's go over here. And then step 3, you can guess what happens. This water molecule, he actually goes over here. That bromine swoops in and takes that hydrogen. So we have an H, and then we have an HBr. Okay, so does that make sense? he goes over here. That's step 1. And then step 2, hydrogen pops off because oxygen has 3 bonds. It wants 2 bonds. And so the hydrogen goes away. The bromine catches it, and it becomes an HBr. And so that was a multi-step process. It takes 3 steps to do that. And of course, the last one, number 9, is this possible? Say no, just say no. This is the aerial. And they're always bad for SN2 and SN1. So no, SN2 or SN1. So if you see aerial, just throw it away. If you see vinyl, throw it away, okay? No SN1 or 2, okay? So now we have to find out which reactant, which one of these guys is going to be number 1 for reactivity, and it's going to be reacting with this guy, right? So is this going to be SN2 or SN1? Well, first of all, I noticed that I'm neutral, so for sure, most likely I'm going to be doing SN1 reactions. Alright, so which one of these guys in an SN1 process is going to be the fastest? Well, again, reactivity, it goes down like this. And so over here, you're going to have reactivity. So the iodine is going to be the best one, right? So you're going to have the best, right? And so for sure, I'm going to ignore bromine, chlorine, and another chlorine. I'm going to be focusing on iodine first, okay? And recall for SN1 reactions that a tertiary is better. However, an allylic is going to be better than a tertiary. That's going to be better than a secondary. That's better than a primary. And that's better than a aerial or vinyl, right? And of course, these guys fail, right? And so what am I looking for? Well, this one is a what? Over here, that's going to be a 1, 2. This is going to be a secondary. Over here, we have a 1, 2, 3. That's going to be primary, looking good. 1, 2, and 3. That's going to be primary. And so for sure, it's going to be one of these two. But I'm going to pick this one first. Why? Well, this one has a vinyl group. Or not a vinyl group, I'm sorry. This one has an allylic group. An allylic group, it means that the neighbor carbon, not this carbon, that's your parent carbon, the neighbor carbon is double bonded, right? So it has a double bond. And so that's really good. That's going to be allylic. And so that's going to be number 1. Now, over here, is it 2 or 3? Well, it's going to be, what? It's going to be this guy over here because it's tertiary. So it's going to be number 2. This is going to be number 3. Now, am I looking for bromine or chlorine? Well, I go up 1. So bromine is not as good as iodine, but it's better than chlorine. So we're going to say that that's number 4. And now I'm looking at this one. Do I want a secondary carbon or do I want a what? Or do I want a primary carbon? Well, I want a secondary carbon. So it's going to be number 5 and this is going to be number 6. Pretty cool. For these problems, I want you to do them on your own and tell me if it's going to be SN2, SN1. If it's an SN1 reaction, I want you to draw out the mechanism and all the steps, right? So if you have a chiral carbon, then you're going to have to do R and show me all the steps for R. If you do have an S, you're going to show me all the steps for S, right? And let's get into it. Okay, so by the time you already played the video, you would have already attempted these problems. So let's get started. So this is already a metal, so that's going to be positive. This is going to be negative. So automatically I'm thinking that this is going to be an SN2 reaction. SN2 reaction. And if you wanted to do the SN2 reaction, by the way, this is a what? Primary carbon. And so, you know, it's not as good for SN2 reaction, mainly because it's primary, right? Oh, I'm sorry. I get them confused. So it is pretty good for SN2 because it's primary. And so if you wanted the reaction, it's going to be a one-step reaction. You just have the OCH2, CH3. All right. This is aerial, so it's garbage for SN2 and SN1. So you're going to say no reaction. Okay. And over here, you have a neutral compound and neutral reactant. So it's going to be most likely SN1. And is that chiral? No, it's not chiral. And so if it's an SN1 reaction, you're going to have 3 steps because it's a multi-step reaction. It's also unimolecular, right? So over here, we're not messing with him. The bromine goes off. That's going to be forming the carbocation. That's going to be step 1. That's going to be H2O. That's going to be step 1. Afterwards, this carbocation attracts the oxygen, so he goes over there. Using my arrow pushing, we have an oxygen with some hydrogens and a bromine still hanging out. Afterwards, this bond breaks, that hydrogen pops off, that bromine collects it. That's going to be step 2. It's also slow. And then you have an oxygen with a hydrogen and HBr. It's going to be step 3. Cool. Afterwards, we go to this problem. Well, first of all, you have what? You have a anion. Because this sodium is positive, that means that this sulfur is going to be negative. And so this is actually going to be SN2 reaction. And you draw your carbon skeleton first. SN2 reaction, you don't have a racemic mixture. So if you have R, which is what I believe you have, let's see, 1, 2, 3, and 4, that's going to be, yeah, R. Well, I'm expecting an S configuration. And so we're going to invert the center. So the hydrogen goes in the front now, and the wedge, or the hash, is going to be sulfur, C, and then like 3 H's. And if you were to do the prioritization, that's going to be 1, 2, 3, 4. It looks like an R, but the hydrogen is in the front, so it's going to be an S configuration. And so that's actually going to be SN2 reaction. It's going to be 1 step, right? Okay, for this one, you're working with a neutral molecule, so most likely it's going to be SN1 reaction. And we have a lot of white space, so we can work it out. Over here, you can get an R configuration. You can also get an S configuration since we are chiral. So we're going to do both processes. All right, so the bromine was on the wedge. It's going to go off. That's going to be step 1. Okay. Now we form a carbocation. That's going to be really slow. It's going to be the rate determining step. I know I'm repeating myself, but repetition is mastery for you and me. So let's put this wedge. Let's give us this sulfur HCH3. We have a hydrogen, right? And a bromine just hanging out. It's going to be step 2. Okay, and also we can have the sulfur coming like this. And a CH2. CH3, sorry. So it's kind of like the other way to do it. And over here, finally, this sulfur shoots off a hydrogen. And it goes like this. This bromine picks up that hydrogen. That's cool. That's how it should look like on the exam if you're doing a free response. So now we have HBr. Okay, so over here, this bond breaks, gives the electrons to sulfur. The sulfur stays in place. And this bromine picks up that hydrogen that was shot off. So we also have HBr. And if you were to do a prioritization, which is a doozy, we were to do 1, 2, 3, and 4. This is going to be R configuration, right? Over here we had a 1, 2, 3, and 4. That's also R. So that's R. We have 1, 2, 3, and 4, that's R, but the hydrogen is in the front, so it's going to be S. And notice that that is a racemic mixture. We have a 50% of getting R and a 50% chance of getting S. Okay, so that's the reaction for chirocarbons in SN1 reaction or SN2 reactions in this case. That's an SN2, and all this was an SN1 reaction. Also, before I wrap up SN1 reactions, it's important for you to know that for SN1 reactions, they're going to be really reactive or really sensitive to polarity. So when you ever have a solvent, let's say a solvent of hexane, is going to be very sensitive to it. So it's going to be sensitive to polarity. So it's going to respond faster, it's going to work better in polar solvents. So it's going to be better. This is important if you're on like a ACS exam or for a kind of like a big national exam. It says, well, in a polar solvent, is it going to be SN2 or SN1? Well, it's going to be SN1 because it's in a polar solvent. It's going to be more reactive to polarity, right? And also, SN1, if you see something like on a national exam, if you have this guy, which is a silver nitrate, well, you're probably wondering, well, is it negative or is it neutral? Well, just know that SN1 is going to be very happy with silver nitrate, AgNO3. And AgNO3 allows us to kind of like make the substance a little bit more slippery per se. It's not slippery in real life. It's just kind of like a slang that I use. It just speeds up the reaction. And so if you have a reaction that would not naturally take place in like 10 seconds or whatever, it would take like 5 hours to do a reaction. Well, you could just put some silver nitrate and it's going to take like a minute or maybe 50 seconds, right? So it's going to allow us to speed up the reaction for SN1. And really that basically concludes the SN1 reaction. And so I hope that you understand SN1 a little bit better than you did yesterday. Moving on, after SN1, we're actually going to do E2, and after E2, we're going to do some E1. And after that, we're going to bring it all together, and I'm going to show you the big picture, and you should be fine for chapter 6. All right, let's move on. So now I want you to find out for these molecules if it's going to be an E2 or an E1 reaction. And sometimes you might even have a SN2 or SN1. So this whole exercise is going to allow us to really find out which one is the preferred reaction, right? And before we actually get into it, I'm going to teach you about E2 and E1 reactions. All right, so what is an E2 reaction? An E2 reaction. So imagine that chemistry is like playing baseball or like playing a sport. Well, sometimes you have your players. So right now we have two players. We have player SN2 and we have another player SN1. So yeah, sometimes SN2 is for negative substituents or negative these guys, right? And so player 1, he's going to be really good with negative reactions. But sometimes you don't have negative reactions. Sometimes you have neutral reactions. And so player 2 is going to step in for SN1 or SN2. And so SN1, which is our second player, is going to be playing our game. But sometimes you don't have SN1 or SN2. So both players are out. So what happens? Well, player 3 is E2. And sometimes he steps in for SN2. And then if E2 doesn't work, well, sometimes you have E1. And in total, you have 4 players, and they're going to substitute for SN1 and SN2. And how do we find out what is E2? So that's the main analogy. That's the main point. Well, here's what you should do. If you're anionic, so again, this has to be anionic, right? So that's anionic for E2, right? Now, it's important for you to know that, remember the allylic or the tertiary carbon, secondary carbon, primary carbon, etc. You know how that mattered for SN2? Well, it doesn't matter for E2 because E2 you're actually eliminating. And so if you're eliminating, you don't care about what's attached or what's not attached. So E2 is going to occur for it usually occurs for this. So if you have a secondary carbon, well, you can have an SN2 or an E2. Well, if you have a tertiary carbon, remember that tertiary carbons for SN2, that fails. That fails for SN2. But E2 says, I don't care, I'm gonna eliminate it. So for tertiary carbons, you're always gonna have an E2. So this occurs whenever you're dealing with a negative component and you have a tertiary carbon. And so that's when you're gonna have an E2 reaction, right? That's an E2 reaction. Now, for E1, notice that this goes for SN2. So we are the substitute player for SN2. And for E1, you're going to be a substitute player for SN1. And notice that E2 and SN2, they're going to be bimolecular. So if I said, I'm increasing one component by 2, and I'm increasing the other component by 3, you're going to have an overall increase of 2 times 3, which is 6, right? So that's kind of like the main thing. That's just how you differentiate between E2 and SN2. Now to differentiate between E1 and SN1, well, again, you're going to have to be a what? You're going to have to be neutral, right? You're going to have to be neutral. And again, it's kind of like a blend. It's kind of like sometimes you can do SN2 or you can do SN1. Notice that for secondary carbons, you could do SN2 or E2. And it's kind of like a blend. And so these components are competing whenever you do a reaction for secondary carbons, right? Same thing is true for E1, but over here, well, for a tertiary carbon, most likely you're going to have kind of like an E1 reaction for that, because recall that for SN1 reactions, the tertiary carbon's pretty bad, right? I'm sorry. So tertiary carbon's pretty good for SN1. So E1 could also be for tertiary or SN1, and so really you're going to be competing for preference whenever you do a reaction, right? And so that's kind of like you're going to have to figure out which one is going to be more preferred, but you're always going to have a competition between E1 and SN1. But what happens when you do a reaction with a E2 or E1? Well, we're going to have to find out, right? Also, on a standardized exam, the reason why for E2, the reason why we don't see E2 reactions for primary carbons is because SN2 reactions happen really, 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 really quickly for primary carbons. And it's so fast that E2 cannot compete. But E1 and SN1, they can compete whenever you have a tertiary carbon. So these can compete for tertiary carbons. And as always, if you see a vinyl or an aerial, well, that's garbage, and you're never, ever, ever going to react with SN2, SN1, E2, E1. It never reacts. It is just garbage. Throw it away. No reaction. Period. Okay? So, no reaction. Okay? Cool. So, let's actually get into the spicy chemistry. Spicy boy chemistry, right? That's what we're here for. Okay, first of all, I don't see any metals, so I'm going to assume that this is a neutral compound. So, it could be SN1 or it could be E1, since we're neutral. All right, now over here we have a 1, 2, 3, right? So what I'm seeing here is that our parent carbon is attached to 1, 2, and 3, so it's a tertiary carbon. Oh man, so it's a tertiary carbon, so it's a toss-up between SN1 and E1. And let's see here. Since I want to show you an E1 reaction, I'm going to do E1 first, and I'm going to do it in purple. So first of all, you're going to draw your main structure first, right? This bromine, since we're doing an E1, the E stands for elimination. And so for an E reaction, it could be E2, E1. Well, your bromine or halide is going to be completely eliminated. So it's destroyed somewhere. Well, not destroyed, but it just gets shot off. It shoots off somewhere, okay? We still have that. And you're going to replace something with a double bond. Okay, well, what am I going to do a double bond? Am I going to put a double bond here? Or am I going to put a double bond there? Or there? Or there? Oh, so many possibilities. Oh, no. Actually, it's pretty simple, pretty straightforward. We are going to prefer the double bond there. How do I know that? Well, I know this because of a Russian dude back in like who knows when. He was called Zaitsev, and Zaitsev's rule actually it tells you which is the preferred structure. So Zaitsev actually says that if you have a molecule that is more substituted is going to be more stable. So the more substituted you are, the more stable you become. Now, to break down Zaitsev's philosophy, what he's really saying is that, hey, look, little dude, you see our double bond? How many lines are connected to our double bond? We have 1, 2, 3. 3 lines attached to us. So it's going to be triply bonded. Not 30, but just 3. Well, compare that to what? If I had that right there, if I had my double bond over there, then I have what? I have 1, 2. So that's going to be 2. Also, we can have this. But is that good? Do I want 1, 2? Well, no. You know, I'd rather have the higher number. That's a triply substituted molecule. So that's a really easy way to do Zaitsev's rule, okay? So this is going to be more stable for an E1 reaction or E2 reaction. In this case, it's E1, right? Because we're neutral. And really all I did was I said, okay, so there's a double bond, and here's a bond attached to my double bond. And if I go to the north side, I have a bond and another bond. And so in total, I have 3 carbons attached to me. Over here, I only have 1, 2 things attached to me, and over here I only have 1, 2 things attached to me, to my double bond. And so I'd rather have a triple than a double substitution, okay? And so actually, before I erase it, this is called the major, this is called the major product, and this is called the minor, or minors, okay? So that's just kind of like a tidbit. I know a lot of books kind of like mess up on Zaitsev's rule, but that's the easiest way that I can break it down for you. So yeah, it's not too bad actually. Okay, so that was doing E1. Can we do SN1? Well, say yeah, we can do SN1. Is it chiral? No, but it's tertiary and it's neutral. So let's do an SN1 reaction. So draw out your carbon skeleton first. You have that. Okay, so that bromine gets out, and well, I'm not going to draw all the steps because you should practice it. You can pause the video and draw out the steps for confirmation. But the bromine pops out, we form a carbocation. The OHCH3 comes in, the hydrogen is still attached to the oxygen. Then the hydrogen pops out and joins with the bromine. The bromine grabs the hydrogen, I should say. And then the oxygen just has the OCH3. Okay, so that's what you should be seeing in an SN1, which is a multi-step reaction. Okay, and there was no inversion because this is an achiral molecule. Okay, moving on. What about the second one? Is it SN1, SN2, E1, E2? Well, over here we're neutral, so it could be SN1 or SN2. You see that? I narrowed it down. I said, well, we're neutral. It could be SN1 or it could be it could be E2. Or sorry, it could be SN1 or E1 since it's neutral. Well, we have a carbon that's attached to 1, 2, 3. Oh gosh. Okay, so it's a combination between E1 or SN1. Okay. Well, let's do E1 because I want to show you how to do one for cyclical compounds, right? So draw your skeleton first. Ooh, that's a pentane. And over here, you should still have the methyl group right there. So this bromine got destroyed somehow in this E1 reaction. So that bromine got taken out. We have the option of doing what? we have the option of doing the double bond. So in an E1 or E2 reaction, you must have a double bond somewhere. Now, the double bond is not going to be here or there. That's dumb. It's going to be in the immediate vicinity where the bromine left or the halide left. So it's going to be here, there, or even here. Okay, so we have to figure out which one's going to be better. Well, first of all, I'm going to tell you that if I did a double bond here, or if I did a double bond there, they're the same. Okay, so for a cyclical compound, it's going to be the same direction. So that's a repeat right there. Now this is going to be different, right? So am I going to prefer that? Well, let's see. We have 1, 2. We have 2 things attached to that double bond, so that's not that good yet. Let's check. What about over here? We have 1, 2, 3. Hey, that's pretty good. That's going to be a major molecule. That's going to be a major structure. Okay, what about the double bond over here? Well, we have 1, 2, and 3. Again, that's 3, and so it's the same thing. 3 and 3 is the same number, so that's the same compound. And so if you're an up person or if you're a down person, it doesn't matter. I'm pretty lazy, so I'm going to leave it up. And so that is a triply substituted molecule. And for an E1 or E2 reaction, you're going to have a double bond, and you're going to lose your bromine or halide. So that is a E1 reaction. Okay, but you could have done an SN1 reaction. And so the bromine leaves, it makes a cation, that's the slowest step. The oxygen goes into this part, this is step 2, with everything, right? So this whole guy moves in here. Oxygen has 3 bonds, it shoots off a hydrogen, so it's going to have 2 bonds. You now have O, and then CH3, and then that hydrogen is grabbed by the bromine, you have HBr, and so that's 3 steps. I just don't want to write it out. You should have written out in the practice problem when you pause the video and stuff. So that's a SN1 reaction. Over here, well, there's a metal and there's a oxygen, so it's going to be anionic, it's going to be negative, so it's not going to be SN1 or E1. It's either SN2 or E2, sorry. So either SN2 or E2. Now we count our carbons. We have 1, 2, and 3, so it's going to be a triple bonded. And so remember that SN2 says, well, I can't work with tertiary carbons because that's too much steric strain. There's too many things bumping into me, so you're going to have to take it away, E2. And so E2 pats SN2 on the back and says, I got this. He goes up to, the batter, right? And so he's going to do a home run. So E2 takes over and he starts playing the game. So E2 is just the E1 reaction, but for SN2. So that's it, really. So we draw our carbon structure. We're not messing with anything. The only thing that we eliminated, which is the E in E2, we eliminated the bromine. So bromine should not be there. So now we're placing our double bonds. Where am I going to put it? Am I going to put it here? Am I going to put it here or there? Well, this right here is not possible because it's not in the immediate vicinity. So am I going to put it here? Well, if I did that, I'm going to have 1, 2 things attached to me. That's not good. What about here? I'm going to have 1, 2 things attached to me. That's not good either. What about here? I'm going to have, I'm going to have 1, 2, and 3 things attached to me. And that's pretty good. That's going to be a major component. So it's going to be a tri-subbed, right? So it's going to be tri. It's going to be the best. And notice that SN2 and E2 are not going to be competing because SN2 is not possible. There are too many carbon attachments to us, okay? So that was an E2 reaction, right? Just for clarification, that could be SN1, it could be E1, and this one right here is only E2, right? Now for this one, what do we have? We have what? That's a negative, so it's going to be anionic, and we check our carbon, so that's a 1, 2, and 3. Okay, again, that is what? E2. It's E2 because we are anionic, means that we're negative, and then we have a tertiary carbon. So tertiary carbon, that's going to be E2. Pretty cool. Same shebang, right here. Bromine is eliminated, right? And I'd rather have my double bond over there because that's going to be tri-substituted. That's 1, 2, and 3. That's going to be tri-substituted. That's going to be the best one. And it doesn't matter if you had the double bond up there. It doesn't matter. It's going to be the same thing. However, this is bad. That's di-substituted. Not good. Okay. What about this one? This is a negative. So it's going to be anionic. It's either SN2 or E2. Right? So we have 1 and 2. That's going to be not di-substituted, but it's a secondary carbon. Okay. So since it's a secondary carbon, it could be either SN2 or E2, so both players can play the game. And so let's do an SN2 reaction. And remember that SN2 reactions, well, they actually occur, they occur, how should I say, in one step. And over here, you can actually have the, O and A, or whatever, the oxygen CH3 go to the bromine. And so, for instance, you have an implied hydrogen right there and a bromine. Well, that OCH3 is going to be able to, well, I should say that this is a stereo center. Obviously, this is chiral, so it's going to have an inversion. And so this hydrogen is actually going to be in the front, and you have an O and then a CH3. So that was an SN2 reaction. I'm sorry that it was a bit sloppy, but I was thinking on the spot. Right? But then again, you could have that this bromine could be eliminated. And if we eliminate the bromine for the E2 reaction, am I going to have my bond over here? Or am I going to have the bond over here? If I have the bond over here, then I only have one group. However, if I have the double bond right here, I have 1 and 2. 2 groups. And so I'd rather have the di substituted than the uni substituted, right? So the di substitution is really good for E2. So that's the E2 reaction. This is going to be the best one. This is going to be the most stable. Okay? Now, this is the mess, and it kind of brings into light the cis and trans aspect for cyclical compounds. And notice that we are neutral, and since we're neutral, we cannot do SN2 or E2. We can do SN1 or E1. So to see what we're doing, we have to find out how many carbons we're attached to. So this bromine is going to be our main person, so we're going to be judging off of this. Alright, so over here we have 1 carbon that's attached to us, 2 and 3 carbons. Okay, so that's 3 carbons. So for sure it's gonna be like an E1 or SN1 blend. But I want to show you the E1 component. So the E1 component, notice that my bromine is gonna be in a what? Is gonna be in a hash. And notice that this hydrogen is in a hash, right? And also notice that this other hydrogen is in a hash as well. Well, since my hydrogens are in the same direction as the bromine, meaning that everything is hash, so hydrogen is hash, bromine is hash, hydrogen is hash, well, that's going to be cis. And it's important for you to know that on exams, cis is really good for E2, or sorry, for just E reactions. And so relative to this guy right here, we have what? We have that something is cis over there, and this is neutral, so it's going to be E1, so cis is good for E1. Okay? And since it's good for E1, what I'm saying is that over here, as a methyl group, this bromine is going to be eliminated, and since we eliminated it, you should really be anticipating also the D right here is going to be deuterium, which is just acting like a hydrogen. It's just like a heavier version of hydrogen. Don't worry about it right now. Okay, so that's deuterium, right? Now let me just make my bonds right there. So that's a methyl group that you see over here. This is also a methyl group right there, and that's deuterium. Okay. So because cis is good, we can actually make a double bond here, 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 or there, maybe, or even there. But which one is the best one? Well, I'm just going to tell you straight up, it's going to be this one, or it can be that one. Why? Well, if I did the first one, I'm going to do 1, 2, 3, 1, 2, 3, or 4. So that's 4 of them. That's really good. Okay, I could do that. So we can have 1, 2, 3, and 4. So that's the best one. That could be a tetra substituted. So tetra is like really stable. It's really good. So for an E1 reaction, that's going to be super good. If you're a up person or if you're a down person, it doesn't matter. It's the same. As long as you don't do like this, then you're going to have 1, 2, bad. If you do that, it's going to be 1, 2, that's bad. If you do this, it's going to be 1, 2, that's also bad. Okay? And so what the example is trying to show you is that if you have a cis relationship for E1, that's really good, right? It doesn't matter for SN1. If you want the SN1 reaction, then it would be like this. Well, you can have the, well, you know the drill, right? So we have OCH3, and then we can have a methyl group in the back, right? And then you can also reverse it so that this methyl group stays the same, but you can put your OCH group, CH3 group in the back. So that's going to be like a SN1 reaction. It doesn't matter about cis or anything, right? So that doesn't matter. But for E1, it does matter, okay? And I'll show you in the next one, or in the upcoming examples. So over here, are we going to be E1, SN1, E2, SN2? What is it? Well, first of all, this is anionic because there's a metal, and so this oxygen is going to be negative. And so if it's negative, it's either going to be SN1, or sorry, it's either going to be SN2 or E2. All right. So let's look at what we have here. What do we have here? Okay. Well, hydrogen is going in the back. Bromine is going in the back. Hydrogen is going in the back. Okay, cool. So that's going to be what? That's going to be a cis relationship. And so cis is good for E2. So cis, good for E2. So it could be it could be an SN2 or E2, but we have to make sure if it's actually SN2. So relative to this carbon, we have 1, 2, and 3. Oh no. Well, first of all, that's a tertiary carbon, and so tertiary carbon for SN2, that's going to be really sterically cluttered. And so if it's sterically cluttered, it's not as good. And so we cannot be SN2. The only option that we have now is E2. Okay? So it's going to be E2. Okay. So that's really bad. Cyclohexane. Let's put our deuterium right there. It's not going to be reacting. Let's put our methyl group. It's not going to be reacting either. But now we have a methyl group right there. The bromine was eliminated, and so we have to put our what? We have to put our bonds. But notice something, that for cis, it could either be up or down. And for trans, you're going to see in the next problem, it's going to be a little bit different. But for cis, it's going to be up or down. And, you know, I'm just going to leave it up for just randomness, right? But what about this one? Over here, we're anionic, so it's either SN2 or E2. Well, it's cyclical, so I already showed you that it's going to be tertiary. Tertiary for SN2 sucks, so it's going to be E2. All right, so this is E2. So we're going to have to check if it's cis or trans. Well, hydrogen is in the back. Bromine is in the back, so that's good. But what about this hydrogen? That's in the front. That's a wedge. Okay, it's going up. Everything else going down. So that's not good. That's not good at all. That's actually trans. So what does that mean for us? Well, it means for us that whenever we're making this reaction, you can no longer put the double bond here. That's not possible. All right. It's really complicated, but it's not possible to do it. So to explain it, if you're trans, whichever atom is messing up your symmetry or your cis-trans relationship, you cannot put a double bond there. So this bottom hydrogen is messing up our cis relationship, so we cannot put a double bond on it. Instead, let's see, you can only put, and you know what? I realized that I made a mistake. It's a pretty bad mistake too. Gosh, okay. So, I got this wrong. I don't know what I was thinking. So cis is actually really bad for E1, E2. So cis is bad. And I'm really sorry for that. However, trans is good. So trans is good for that. So it could go up or down, right? But if this were a cis, what would happen is that over here, we're messing up because we're all cis. And so the only one that's possible to be, to be eliminated is not necessarily the bromine, but it's going to be the deuterium, whatever. And so the deuterium is going to be eliminated. So it's kind of like a weaker hydrogen per se. So that hydrogen, that deuterium, is going to be kind of shot off, right? It's going to be shot off. And yeah, that's all you need to know. I'm really sorry for that. That's really embarrassing for me. So to really set you straight, I'm gonna just kind of like recap. So whenever you have cis, that's gonna be bad for E1 and E2. You cannot put your double bond up or down. However, since we're working with deuterium, that's kind of like a weaker hydrogen, you're gonna put your double bond upwards, and that double bond is gonna eliminate the deuterium. Okay, it's gonna eliminate the deuterium, right? And over here, since we're trans, that's good, and so you could go up or down. You could do this one, or you could do that one, right? So to really set this in stone, trans is good, and cis is bad. Okay? So that's kind of like the reaction that you should be expecting, right? And it's even more important for you to know that for E1, should really eliminate that. That cis is bad for E2, but it's actually pretty good for, yeah, it's really bad for, to explain this. But cis is good for E2, for E1. So this is for E2. But for E1, you're going to have that, cis is good. Okay? So for E1 reaction, cis is pretty good. So it could go up or down, right? But for E2, cis is bad. Right? So that's kind of like what you need to know. But anyways, I don't really think that's going to be on the exam. If it is, then you know that E2 transit's good, cis is bad. E1 cis is good, right? And maybe you can extrapolate that maybe trans is bad. Okay, so let's move away from this train wreck that I completely kind of steered you wrong. I really apologize for that. Let's move on. Okay, for this one, let's say that I want to react via an E2 reaction. If I want to react with an E2 reaction, notice something that is a bit off, right? So something's a bit off. And that thing is that we are in what? Well, it's not very obvious, but bromine is on a wedge. And over here, hydrogen is on a wedge, which is not good. So we have a wedge, and so that's going to be cis. And for E2, cis is bad for E2. And the reason why we're E2 is because we are negative. So metal is positive, that means hydroxide has to be negative. And since we want an E2 reaction, not an SN2, let's say that's an exam question, and we want to react, but how can we react? Well, what if I rotated this bond, right? So what if I rotated like this? So I'm not moving anything like that. To be more elaborate, I guess. Right? What if I did this? What if I had bromine right here and a hydrogen? And remember that whenever I rotate something, whatever was a wedge becomes a hash. And so over here, my wedge now is going to be a methyl, and my hash is going to be a hydrogen. Okay, so now we have a bromine and a hydrogen. Bromine is trans to hydrogen. So trans is good for E2. Okay? Right? So now, what can we do? Well, to do an E2 reaction for sodium hydroxide, we can eliminate this bromine. And whenever we eliminate this bromine, what is left is that, well, we just have a hydrogen, right? So we have a hydrogen right there, and it's going to be implied, right? So that's a hydrogen. We have a methyl group. This hydrogen is implied as well. And do I want my bromine, or sorry, do I want my double bond right there? Well, I'm going to have 1, 2. That's going to be really bad. Do I want it over here? Well, I'm going to have 1, 2, 3, and 4. And so, I'd rather have it like this. So you could say that's hydrogen. This is going to be a methyl group. So that bromine was eliminated. We had to twist the molecule. We have to twist the bond so that we're not cis-cis. We have to be trans, right? So trans is going to be good for E2. Cis is bad for E2, right? And so whenever we twisted it, hydrogen is in the back, bromine is in the front now. So they are trans. We can eliminate this bromine. That's what you do for these reactions. Of course, we're using bromine a lot. You can do like iodine, chlorine, etc. So bromine is eliminated. We put our double bond where we get the most substitution. So over here, we're going to have 4 things attached to that double bond, and that's really good. And I guess it doesn't matter if it's cis or trans for E1. So the cis and trans only matters for E2. Cis is bad for E2, trans is good for E2. Okay, that's how it should be. That's set in stone. Just roll with it. E2, you're going to have to put in the cis and trans relationship. Okay, there we go. So now for the final one, right? For the final shebang, we're going to do 9 practice problems that ties everything together. So for these problems, you're going to have to say, is it SN2, SN1, E2, or E1, right? And draw each reaction. So if it's SN2 and E2, you're going to have to draw each reaction. All right. For this one, we are negative. So this is the anion, so it can either be SN2 or E2. Over here, we're primary. And so primary SN2, that's pretty good. So it's just going to be SN2. Why? Well, SN2 is really fast for primary, and E2 is pretty slow, right? And it's not going to be able to compete. So whenever you do this, is it a chiral carbon? No, it's not a chiral carbon. So it's just going to be just your basic reaction like that. So that's your SN2 reaction. SN2 reaction. Over here is a negative. So that's a negative. It could be SN2 or E2 automatically. Well, that's a 1, 2, and 3. That's a tertiary carbon. So that's going to be what? That's going to be E2. And for E2, it's going to eliminate the bromine. So first, draw your carbon skeleton. The bromine was eliminated. Do I want to put my double bond here? Do I want to put it there or there? Where do I want to put it? Well, I want to put it over here because I would get 1, 2, and 3. 3 substitutions, right? Compared to 1, 2, 1, 2. Compare that to just 1. And so this one is going to be the major one, and then the minor one is just going to be 1, right? So this is going to be a triply substituted molecule. Okay. Over here we are negative, so that could be SN2 or E2. Over here we have a double bond, or not a double bond, but it's a secondary carbon. And so it could be SN, I'm a little ahead of myself, sorry. Not ahead of myself, but I did it wrong. So this is a secondary carbon. So it could be SN2 or it could be E2. So you really have a blend. They're going to be competing for each other. So in some solvent, like let's say you had a gallon of this experiment, some of them is going to be SN2 reacting, and then some of the experiment is going to be E2 reacting, right? So they're going to be competing. For the SN2 reaction, it's pretty simple. It's just going to be a cyclopentane right here. The iodine gets substituted out. So we have an OCH3, and we have not an H, but an iodine with a sodium, right? And then for E2, it's going to be a cyclopentane. The iodine is completely eliminated. It's completely eliminated, right? And you don't care about what happened here. This is going to be E2, so we don't have anything hanging out. It could be here, the double bond, or it could be over here. So I'm just going to leave it like that. So that's going to be E2. This is SN2. This is going to be E2 reaction. Notice that there's no oxygen hanging out. We eliminated iodine. That was our mission, so we just leave, right? Mission accomplished. Over here, we're neutral. So I'm not SN2 or E2. I'm actually SN1, or I could be E1, right? Right there, we have a secondary carbon. So that's also secondary carbon. And, well, you could, for instance, you could be SN1 or E2 or E1. So for SN1 reaction, the bromine would leave, and you're just gonna have the oxygen like this, and then it's gonna have like its ethyl group, and then this hydrogen is gonna leave, or I should say this bromine is going to pick up that hydrogen. So really, in 3 steps, you just get that, right? So on your piece of paper or whatever, draw out the 3 steps for SN1. I did it a lot of times. You should know it by now. Or you could do the E2. So this is SN1. And you can do E2, or E1, sorry. So it's the same thing as above. It's just going to be like that, right? So hydrogen or oxygen doesn't it doesn't how should I say, it doesn't connect to us, and so E1 just gives us a double bond, and it could be going that way or it could go up there. It's going to be the same thing, right? Over here we're neutral, so SN2 or E2, right? Then we have what? We have, to this carbon we have 1, 2, so that's going to be secondary. But notice that this is actually a vinyl, or not a vinyl, this is actually a allylic. So allylic is really fast, and that's really fast. That's going to be really good. So it could be SN1, or it could be E1. So for conveniency, we're going to be erasing a lot of these stuffs. A lot of stuff right there. Okay. So we can have cyclohexane with a double bond, so it's a cyclohexene. And for SN1, well, this bromine gets transferred out, it's substituted. That's what the S stands for in SN1, right? We're eventually just going to have an OH right there, and then an HBr. That took 3 steps. Or you can do the E1. So this is SN1. The E1 is like this. You have that. And do I want something that goes here? Do I want a double bond like that? Well, you should just say no. You want a double bond like this, right? So it's just di-substituted, and it doesn't look as weird, because normally whenever you see rings, you don't see rings like whatever, right? You don't see it like this. Yeah, I've never seen a ring like that, especially like a phenyl or benzyl. So just kind of like skip a space and put your double bond whenever you already have a double bond in a ring, okay? So to make this a lot cleaner, here's your double bond initially, and then you're just going to put another one right there. Over here, we are anionic, so it's SN2 or E2, right? And look, that's a vinyl, right? So the double bond is directly attached to this carbon, so that's a vinyl. And so you're going to say that this is no reaction, it's just garbage, right? Pretty bad. That's all it is. Vinyl, no reaction. Over here, this is also a vinyl, so that carbon, that double bond is directly attached to that carbon. That's going to be a vinyl. It's trash, so no reaction. Okay. Now we have, is this a phenyl with a sulfur? So is that neutral? I would say it's neutral. So it's either SN1 or E1. Okay, so that's 1, 2, 3, right? So that's 3. That's really favorable for SN1. So we have a blend between SN1 or E1. So I have SN1 or E1, right? So for the SN1 reaction, we're going to do it in green over here. SN1 takes 3 steps to do. I'm going to skip a lot of steps. You should know this already. The sulfur eventually just has the SPH. The hydrogen shoots off from the sulfur. It joins with the bromine, and that's the SN1 reaction. And then for the E1 reaction, well, you're not going to be connecting anything. You eliminated the bromine, right? And so we can actually do up here, we can do it here, we can do it here, right? And so which one am I going to prefer? Well, I'm going to prefer, which one? If I do this, I have 1, 2, and 3 things attached to me. If I do it here, I'm going to have 1, 2, 3 things attached to me. And if I have a double bond here, I'm going to have 1, 2 things attached to me. And so I'd rather go up or down. It doesn't matter if I go up, it doesn't matter if I go down. You're going to have 3 things attached to you. So this is going to be one thing, that's another thing, this is going to be another thing. Okay, so that's 3, that's a triple, substituted, that's really good. And for the last one, before I end this video, before I say goodbye, and before I blow you kisses, I'm going to say that this is a neutral, so it's either SN1 or E1, right? And over here you have a, what? You have a primary carbon. So that's a primary carbon. Well, I know that primary is pretty bad for SN1, but you should also know that it's pretty bad for E1 as well, okay? So this is no reaction. You can treat it like a tertiary carbon for SN2, right? So a primary carbon, I don't know why I wrote it over there, so it's going to be no reaction over here, because this is a primary carbon for SN1, it's a primary carbon for E1, right? We're neutral. And so primary carbons always fail. Same thing with vinyls, same thing with aerials, right? So they fail, and there's no reaction. So no reaction, no SN1, and no E1. So now you know how to do SN2, SN1, E2, and E1, right? And you can differentiate when to do it, when not to do it, the factors, the leaving groups, and I hope that this really helped you out. I hope that you understand how to do spicy chemistry, spicy boy chemistry, and that you become a spicy boy as well, or a spicy person, right? And I hope that you do well in your exam, and that you understand reaction mechanisms, and that you remember that SN1 reactions actually have 3 steps to them. And the first step requires that you make a carbocation, which is a slow step. Afterwards, the substrate, which is going to attack us, is going to connect. Everything connects. Afterwards, that substrate is going to shoot off a hydrogen. That hydrogen is going to be picked up by that bromine or iodine or whatever the halide is, and it's just going to be completed. So that's 3 steps just for SN1. And also, whenever you have a chiral molecule, SN1 is going to be what? is going to have a racemic mixture. And so if you have R, you can have R and S. Or if you have S, you can have R or S, right? And so that only occurs for SN1 reactions. E1 reactions require that you eliminate something. Well, E1 and E2, they're the same reactions, they just have different preferences, but they're gonna remove a halide, and they're gonna put a double bond. And whenever you put a double bond, you're gonna want that double bond to have more substitutes on it. The more substitutes you have, the stable it becomes. And so that's basically kind of like a minute recap of what we just did for the last 48 minutes. So I hope you have a great day. I hope you're amazing at chemistry now, and I hope that this video helped you. So I just want to say thank you for watching. So again, have a great day, and thanks for watching.